Hi, everybody. Give me a second while I get my screen up and running for you. Well, I'll just go ahead. It seems to be stuck. Give me one more sec. All right, I'm just going to go ahead. All right, so good evening, everybody. Welcome to tonight's webinar. I am Lori Schiavo, the RSES Senior Director of Operations, and I would like to welcome everyone to part 2 of the HVACR system design webinar. Tonight's session, which I love, you did the load calculations, now what? Which is being presented by Bryn Cooksey. For those of you who do not know Bryn, he has more than 20 years of HVACR industry experience. He's currently the owner and the general manager of Air Doctors Heating and Cooling. He's also an associate professor with Washtenaw Community College in Ann Arbor, Michigan. Bryn is also a training consultant for mechanical contractors, HVACR supply distributors, weatherization agencies, and training organizations. In addition to holding many degrees and certifications, he was recently named, I believe almost in March, right? Correct me if I'm wrong, a top 25 HVACR industry's most influential educator and trainer by ESCO Group. And just most recently, a top 40 under 40 industry professional from the ACHR News. Next presentation is about 45 minutes. Afterward, we'll have a Q&A session, and you can submit any questions you have using the question pane. I'll field those questions aloud to Bryn once I get them. This presentation is being recorded and will be available online for viewing at your convenience. And now I'm going to introduce Bryn. Let him take over as soon as I figure out where he's at. All right, Mr. Bryn Cooksey.
All righty. We'll share our screen here. All right, Lori, can you see my screen okay?
I do not yet see it.
No. All right,
I still see you. Now I see it. The Air Doctors logo in the background there.
Yep. Do you see my presentation?
Right. You got it.
All righty. Well, good evening, everybody. Once again, I'm Brent Cooksey. Let's get started. This session is HVAC system design part 2. You did the load calculation, and now what? All right, our learning objectives for tonight. We're going to talk about the different functions of the components of a forced air warm system. We're going to demonstrate common diagnostic and assessment methods for ducted distribution systems. We're going to talk about common problems for each type of distribution system, and then we're going to talk about some solutions to these problems. All right. So in a nutshell, if we narrow our focus, we're going to talk about existing duct systems, how to test them, how to resolve those problems, and then kind of get technicians in gear on how to measure for these different problems that we're going to talk about tonight. All right, the basis of this presentation came from the standardized weatherization curriculum provided by the Department of Labor, and also a study that we did internally in 2021, and we'll talk about that study now. All right, so if we remember from our first session, we have a kind of a unique problem here in the United States. We are about 16% of the world's population, but yet we consume about almost 5%, between 4 and 5% of the world's energy, which, let me restate that. We're about 4% of the world's population. We consume about 16% of the world's energy. So if you look at these two pie charts here, you'll see that our population size relative to our energy consumption doesn't match. And that brings up a big problem. And that problem is energy efficiency. So with this in mind, our industry has a significant problem or impact with those statistics. All right, if you think about it, the HVAC system accounts for about 45% to 50% of the energy consumption in all buildings. Also, it has been studied through Energy Star and other organizations that HVAC systems are commonly connected to poorly designed and installed systems, with the average system being about 50% efficient. So what that means to you and I and the clients that we serve, for every dollar of utility money that we spent on our gas and electric bill, the customer only gets about 40% of usable energy, which uncovers a significant problem. So keys to HVAC system design: you want to do a room-to-room load calculation, and this is what we covered in our Part 1 series, which is recorded for your enjoyment. In this session, we're going to talk more about the duct design. We're going to talk about how it needs to be properly sized, properly sealed, and insulated if necessary. And we'll also touch on some ways to test, adjust, and balance the system. And lastly, HVAC system commissioning. All right, so let's talk about our study. This is our Air Doctors duct repair study that our home performance company performed in 2021. And it's basically just to test how important air distribution systems and how they work are a significant impact to heating and cooling systems. So in 2021, we were physically in about 3,800 houses, the exact total 3,880. And these are clients from our home performance contracting business. We performed a load calculation on each of these customers' premises, and what we concluded that 98% of those customers, or 3,802, had a grossly oversized furnace and air conditioner. The furnaces came in about 20,000 BTUs or more, and the air conditioners were about 1 ton or greater. Right? We also measured the duct systems, and those duct systems we measured their size and capacity, and we would compare it if we did like an ACA manual D duct design. And we found out that those duct systems were undersized about 50% or more. So some common duct issues that we found that they were grossly undersized comparative to the equipment that was connected to them. We also discovered that they were not balanced, they were not sealed, they were not insulated if they needed to be, they were not clean, and when we crunched our numbers, they added about $230 annually to the utility bills that customers pay. So the goal of a well-designed duct system, it provides conditioned air to meet all the room's heating and cooling loads. It provides thermal comfort evenly in all conditioned rooms. You want to make sure it's properly sized so that the static pressure is within manufacturer specifications. You want to verify that the ductwork is sealed so that we get the air to the proper place that it needs to be. You want to have balanced supply and return airflows. And then you also want to minimize your duct air temperature losses between the air handlers and the supply registers. So if you have a good duct design system, this is the actual goal that you'll be seeking when you put that system in. All right, so let's talk about this system. All right, the parts include, you got the air handler or the furnace, you got the heat exchanger, which is used for the combustion process, you got a supply air plenum, you got the branches, you got the supply registers, and you have return grills, and then you have return branches that are connected to the return trunk and return plenum. And those ducted systems pretty much will look like this. There's other arrangements and stuff like that, but for the most part, this is what the ducted system will look like. All right, now, as a contractor, I've seen over many years in different markets how a bad habit that the HVAC industry has gotten into, and it depends on your area, is where a load calculation was not performed and equipment was replaced with the same size. All right? And there was never any attention to the duct system. Now, when we look at the duct system here, the purpose of the duct system is to get the conditioned air from my equipment, whether heating or cooling, and get it to the different parts of my building efficiently. If the duct system is not sized and designed appropriately, I will fail at that. So there's a couple measurements that we take. For years, technicians have always been trained to measure temperature rise at the equipment just to verify that the equipment is working correctly, but oftentimes we neglect the duct system, which is just as important as the equipment. Now, let's run through a scenario where you can use the duct efficiency to actually calculate how well the duct system is operating. So if we look at our formula here, and I'm going to go back to the other slide so we can reference what we're talking about. The duct system efficiency formula is the temperature difference of the furthest supply and return, the furthest terminal unit of the duct system, and it's going to be divided by the temperature difference of the equipment. So the temperature difference, supply and return of the equipment, and the temperature difference of the duct system. And we're going to ratio those and divide them. All right. So let's look at what we're talking about. So remember, my equipment makes my heating and cooling, and my duct system is going to travel that conditioned air to the appropriate place. And what we're saying, the temperature supply or delta T of the equipment, I'm essentially going to take a supply temperature and a return temperature and get a number. And when we're talking about the delta T for the duct system, I'm going to take the supply temperature of my furthest point and my return temperature of my furthest point, and I'm going to get a number. When I get those numbers, I'm going to put those into a formula and get the ratio of those, and it's going to come up with a percentage. So let's talk about an example. So for example, I got a forced air furnace that has a temperature difference of 120 in a supply duct, excuse me, and I have 70 degrees in a return duct. That temperature difference is 50 degrees Fahrenheit, right? So in my supply duct, I got 120, and then my return duct coming down here, I got 70 degrees. You subtract those two, I got 50 degrees Fahrenheit. Next, I'm going to take the furthest supply register, which has a temperature of 94, and the furthest return register or grill that has a return temperature of 65 degrees. And this is going to give me a temp rise of 29 degrees. So let's look at what we're talking about here. All right, so in my farthest supply, all right, we're at 94 degrees. And my furthest return, we're at 65 degrees. When I subtract the two, I have 29 degrees Fahrenheit. All right, here's a duct system efficiency formula. All right, it's a pretty powerful formula. If I take the supply and return of the furthest points, and I divide that by the supply and return of the equipment, I will actually get the duct system efficiency in a percentage. Now, this is a real world example that I would actually pull from a typical job. And if you look, that duct system efficiency is only 58%. So I don't know about you, but when I got 58% in school, that was an F. I got bad grades and I got a talking to. All right, so let's talk about how we can fix that. Well, some people will say, let's throw some really good equipment at it. Let's throw a 98% efficient furnace at it, and that's going to solve all the problems. That's sometimes what contractors will promise customers. So if we use another formula, the HVAC system efficiency formula, we're going to take the equipment efficiency plus the duct system efficiency, and we're going to divide that by 2 to get a ratio, all right, to get an average, excuse me. And that average, let's take a 98% efficient furnace plus a 58% efficient duct system, divide those by 2, and my total system efficiency is 78%. So even throwing some of the best technology we have at the problem, it is still going to be substantially impacted by a poor duct system. And that's what we're after. So the best grade you can get in this situation is a C with this issue. All right. So we have to fix the duct system. The duct system has to be a primary source of focus, because if it's not, the BTUs that you pay that utility company are not going to be delivered into the space. So it's a lot of things that we're going to do, and that's what we're going to cover tonight. How to right size that or make that 58% better, so that way the customers are getting more of the money that they pay for when they pay for energy. All right. So one of the things you want to resolve is open returns. This is something that's pretty critical, especially when it's located by a combustion source such as a draft hood. That can also impact that. That will be things that we look at. All right, let's talk about our system components. All right, we have a forced air furnace here. We have the circulating fan, which is producing our static pressure, our airflow. We have an air filter back here. We have a cold air return, we have the heat exchanger, and then we have our warm air to the house. All right, so we're going to talk about kind of these different components and how they relate to our duct system. All right, the function of the heat exchanger is to take those combustion gases and put the heat energy into the duct system or airflow. All right, the heat exchanger is extremely important. However, a lot of the failures are attributed to poor duct design. Poor duct design. We're going to talk about what some of the average duct systems that we measure, what they're reading at, but a lot of times those cracked heat exchangers come from poor duct design. Now, as a service tech for many years, I was always taught how to visually inspect for a crack, but I never really got the information to understand what was causing it. And a lot of times it was a poor airflow setup. Maybe the ducts were undersized, the equipment was too large. A lot of the stuff that we run into, we're taught how to find the issue, but we're not taught how to find why the issue occurred. All right. All right. Things to help with your ductwork efficiency. Ducts should be sealed and they should be insulated if they're in unconditioned spaces. But there are some caveats there. When we seal duct systems and we didn't appropriately size them, what's going to happen, that duct system is now going to be sealed. And if I had high static pressure to begin with, the static pressure is going to be even higher if I seal those and they're not sized properly. So take that into account. Don't arbitrarily seal ducts unless you truly understand the airflow and static pressure of that system, because you will find cracked heat exchangers, burned out ECM motors. You'll find all these negative consequences as equipment damage because we improperly sealed the duct system. But properly sized ducts should be sealed. Properly sized ducts also should be insulated if they're in an unconditioned space. All right. Now, when we seal the duct system, there's a few different options. All right. You have your mastics and your tapes. You even have specialized solutions like AeroSeal, which can seal the ducts from the inside. Regardless of what your duct system sealing type is, the key is to seal the ducts regardless of where they're located if they're sized properly. All right. Talk about some controls. The controls of our duct system, you have the thermostat. I usually have some type of control to shut the equipment down if I have some heating issues. I can have balancing dampers, which should be on to adjust from heating to cooling. And then I can have motorized dampers, which include the zoning system. Those all have to be taken into account. All right, thermostat is easy. The thermostat provides the control for our system to activate whatever condition we're running into. All right, that was simple. Balancing dampers. All right, so on a true duct job that was done properly, I would have sized my equipment. I would have specified my equipment. I would have performed a duct design calculation. And generally speaking, the airflow is going to be different for my heating versus my cooling. I'm going to size that duct system for the worst situation or the situation that requires the most airflow. And then I will put balancing dampers in, one, to make sure whatever area based on my load calculation sees the appropriate CFM. And then remember, in a different part of the season, let's say if I go from cooling to heating, those dampers will have to be repositioned to make sure that that part of the season gets the appropriate amount of CFM. So balancing dampers are required all the time, and they need to be operated properly. All right. Some situations are calling for motorized, or some people call this a zoning feature. A zoning feature is where I set up a separate control and I use motorized dampers to redistribute the air to create a second zone. This is a solution that's often used to solve maybe like a second floor that's maybe not producing enough heating or cooling. A zoning system typically can be deployed to solve that solution. However, zoning systems have rules, and outside of the context for this actual presentation, they need to be followed, because if those zoning systems are implemented incorrectly, it can cause serious problems as far as equipment damage and comfort when we talk about our duct system. Here are some common duct problems. We have duct leakage, which can leak to the outdoors, which is a significant penalty. We'll talk about that here shortly. We can have a restricted return side. The system cannot be balanced. We can have too high or too low temperature at the heat exchanger. Static pressure, real big measurement, it can be out of range. And the airflow of the air handler can not be matched to the system. And we have to look at, are people living within a distribution system? So are they having comfort issues due to where, if they can be affected, like if we close a door? So we're going to talk about that here shortly as well. All right, here's some diagnostics that you want to keep kind of handy, and these measurements will help you just about uncover any kind of ductwork issue. All right, so we'll talk about the pressure pan. We're going to cover the duct blower or duct leakage tester. We're going to talk about static pressure, temperature rise, room-to-room pressure, and then actually measuring air handler flow. First, let's talk about the pressure pan. Now, this pressure pan test, this is used in conjunction with a blower door. All right, we talked about the blower door in our first lecture presentation, part 1, for the load count. Now, when the blower door is operating, and if I have a pressure pan, I can actually look with this encapsulated pressure pan here, this device, this is a pressure pan, and it's connected with a tube to a manometer. And when I have a blower door running, I can actually encapsulate maybe a supply register or return grill, and this will let me know, it will give me a sense that the ducts may be leaking, and even more important, if they're leaking into an unconditioned space. So for example, let's say the duct that is feeding this pressure pan is located in an attic. If I have a blower door that is making a pressure differential, and I pick up that pressure differential with this pressure pan, that could indicate that air from that distribution system is leaking into unconditioned space. So I get double trouble for that. I get air that doesn't go where it needs to go, and then I have air that I paid to condition leaking into a space that it's not supposed to be at. All right, so that's the pressure pan. This pressure pan helps us figure out, do we have leaking air leaking from the conditioned space outside? And remember, the pressure pan has to be used in conjunction with the blower door. All right, here's a procedure for it. You're going to depressurize the house to 50 pascals. You're going to test each register and grill, and you're going to document the readings. And when you document the readings, you're going to basically put those into a sheet of paper just so you can understand which grills or registers are the worst. All right, you're going to seal the ducts, and then you're going to retest the readings. And remember, again, this is done with the blower door test, and you're really going to find if the ducts are leaking to an unconditioned space. Now, if you want to take note here, the goal is to be lower than 1 pascal, which makes sense. If the ducts were tight, then I'm not losing energy into the space. I would want them to be 0 or at 1, less than 1. If I get a significantly high reading, like close to 50, that duct is completely disconnected and is dumping all the air into an unconditioned space, or is pulling in air on the return side in the unconditioned space. In either situation, it's not a good deal. Okay. So here's a sample duct pattern, basically where a technician is going to test each register location, register or grill, and they're going to record what the reading is in the pascals. Remember, our blower door test pressure is 50 pascals. They're going to go and record each reading to see how it looks. And remember, our goal is to be less than 1. So these readings that are a little higher, that represents that there is some improvement, whether I can seal the ducts in the space, or I might even have boot leakage where the duct register boot is connected to this floor here. Okay. All right. The next thing we're going to talk about is a duct leakage test. A duct leakage test is this system right here, and it basically has a duct blower, or a baby blower door, as my son calls it, and it has a duct that connects to a duct system, and it's controlled by a speed controller or a manometer. All right. When we use a duct leakage test, there are 2 tests that we can perform. We can get total duct leakage. That depends on if I have a certain CFM duct system, it measures how much is leaking totally, which is important. It tells me how leaky the ducts are. And then I can perform a test where I compare the duct leakage Is it inside the conditioned space or outside? And remember, if I have duct leakage to outside, it's a double whammy. I'm not getting the CFM to the proper place, and I have paid to condition that air, and it's being wasted and can never be recovered. Okay. All right. The procedure for the duct blower or duct leakage test is to, one, open a window, and this is for pressure balancing purposes. You're going to install the duct blower to the air handler compartment, or this can be a centralized return. You're going to temporarily seal all the supplies and returns, all the grills and registers. You're going to insert a manometer into a supply duct, and you're going to open up all the rooms inside the thermal boundary that have ducts in them, and you're going to pressurize that duct system to 25 pascals. And when you do that, you're going to read the leakage on the screen. This manometer speed controller is going to control this fan to 25 pascals. That 25 pascals is about what a typical duct system will run at. And the leakage provided on the screen is how much leakage this actual fan and manometer are calculating. Okay? All right. When we test leakage from to outdoors, you're doing a similar test. However, you're going to be running it with the use of a blower door. So in this procedure, you're going to close all exterior windows and doors. You're going to set up a blower door to pressurize the house. Now, that's a distinct difference from a normal test. Normal industry standard is to depressurize. In this case, we're going to pressurize this house and turn the fan of the blower door actually the opposite way. We're going to connect the duct blower, like we've seen in our previous slide, to the air handler compartment, just like we would do a typical duct leakage test. We're going to temporarily seal all the supply and return grills, supply registers and return grills, like we talked about. We're going to pressurize the duct system to 25 pascals, so that hasn't changed. But now we're going to pressurize the house until the pressure difference of the house and ductwork is at 0. All right. So I have my duct system at 25 pascals, and I'm going to have my pressure of the blower door pressurize the house until they have a difference of 0. And what this does, any leaking that occurs in a duct system has to leak outside because the pressures are the same. And we're now able to actually calculate how much leakage do I have outside because it's a double negative. I don't have the conditioner to go in the space I want, and I paid to condition that air and it's leaking outside, and I can never recover it. So this is another test that we need to perform if we have issues. All right. So a third test that we'll talk about is called room-to-room imbalances. All right. What room-to-room imbalances are, based on the operation of the house, I can have things that take air out of the house or put air in. And if I close a door to a particular bedroom or zone, I can have imbalances that can cause issues. So if that's the case, we have a way where we can measure these room imbalances. Now, the reason why these are important is because if I develop a positive pressure or negative pressure, either case, I can affect the HVAC system from operating, and I can also change the building pressures. And why that's important, maybe I get air from an area like an attic where I don't want it. So we need to check room-to-room pressures. So when you look at a typical room, you want to be balanced. In some cases, if the duct system is not designed properly, it won't. I can have where I have not enough supply or too much supply, or not enough return or too much return. All right. So what we do to check this, we do what's called a room-to-room pressure and balance test. And what you want to do, you want to take a high-quality micromanometer like so. And you want to take this manometer and you want to turn on the air handler, the fan actually controlling the system, whether heating or cooling. And when you turn on that air handler, its natural running condition, you're going to go to all the rooms that have doors that can be closed. And you're going to take this manometer and you're going to take this tube and you're going to toss it under the door. All right. When you toss it under the door, this test is going to help you determine, do I have a significant pressure buildup in this room as compared to the house? Right. When I run this test, the key here, I don't want to be over 3 pascals. If I'm over 3 pascals, which is not a lot of pressure, we should remedy that issue by adding supply air to that room or return air, whichever one I need. All right, and once I fix it, I need to retest. So essentially, you will go to each and every room that has a door, close a door, throw a tube on, connect it to a manometer, and come up with a Pascal reading. And remember the trick, I want to be below 3 Pascals. Okay? This will help us determine if a room has an imbalance between the supply and return. One way to fix it, you can do things such as undercutting the door. If I undercut the door, I have some room underneath the door that will help balance the pressure. You can only do that within limits. You can only undercut the door so much. Another thing that you can do is add a jumper duct. A jumper duct is basically you go above the conditioned space, and I can cut in registers here, and I can cut in a register here, and I need to size this like the way I size typical duct systems. And I need to add a duct here that's sealed and insulated if it's in an unconditioned space that will balance the two rooms to reduce that pressure difference of 3 Pascals. I can add a door grill. All right, adding a door grill here, like so, or a wall grill. And these grills basically transfer the air to help reduce that balance to keep it below 3 Pascals. Or I can add the supply or return I need in that room to make sure that the balance is correct. So these are my solutions when I have rooms that are underperforming. So as you get a comfort call and you're trying to assess duct systems, these options that we just talked about will help you identify where in the duct system. Is it a leakage problem? Is it a room-to-room pressure problem? Because it can be sized appropriately, but if it isn't installed correctly, you can still have an issue. So this is another test. This is room-to-room pressure imbalances. That's what this is called. All right. My problem with the duct system can be static pressure. All right, static pressure is nothing more than bursting pressure. It's the bursting pressure, and the way static pressure works, it takes more energy for the air handler to move air if static pressure is high. I get high static pressure, I get low airflow. So static pressure, many training companies equate that to blood pressure, and it is. It's a static pressure reading of the bursting pressure of the ducts. The higher the duct pressure, the less airflow I can move, the amp draw on my fan increases, and also if it is excessively high, it can lead to equipment damage. All right? So how static pressure works, I take a static pressure probe, all right, and I measure the air handler static pressure for total external static pressure by placing it on the equipment and the supply and return. Or if I'm troubleshooting specific areas, I can move that probe throughout the duct system. It just kind of depends on what you're looking for. All right. Static pressure is so important. We now take it on every single service call just because in that same study we conducted, we found that each of the duct systems that we physically walked into had a static pressure of 1 inch and they were not sealed. So that just tells you how grossly undersized they were. All right. For taking static pressure, you're going to check the nameplate for the external static pressure, or TSP, TESP, or ESP. All right. When you check the nameplate, the static pressure number depends on the type of equipment. There are different ratings for furnaces as compared to air handlers or air handlers that have coils in them. So you have to be certain on which piece of equipment that you're working with. You're going to measure both the supply and return sides as the unit was shipped. That's the key. You're going to measure the external static pressure as the equipment was shipped. All right. Or another way to say it, measure at the inlet and outlet of the blower. It's always suggested to have a clean filter in place to get an accurate duct system evaluation, because a dirty filter will obviously affect your static pressure. And if you're going for external static pressure, remember you want to test the equipment as it's shipped. Now, you can use static pressure for troubleshooting, which is outside of the context of this presentation. But to get external static pressure, it gives you a lot of information with one reading. All right. Now, most of the meters on today, you can hook up 2 probes, and it will give you an external static pressure reading. if you don't have that capability, you can simply take the return side and the supply side, add those two readings together. And when you add them together, it's the only function in math that I know of that you can ignore the negative sign. So whatever readings you get, just add them together, and that is your external static pressure. Reason why that's important is because when I do external static pressure, as I mentioned, the higher the pressure, the lower the airflow, right? So if I look here at an external static pressure of about 0.31 inches of water column, all right, I have my full 1600 CFM rated airflow. And if I start to increase that static pressure, and let's say I'm at 0.69, that same fan can only deliver 1350 CFM. So as the static pressure increases, my airflow increases, my performance decreases, my comfort complaints increase. I have a lot of problems by not maintaining that static pressure. Static pressure is going to be a function, is the equipment sized properly? Did they use the right fittings when they were designing the duct system, etc.? So it's more of a bursting pressure size constraint when we're dealing with static pressure. All right. So if static pressure is too high, the airflow might be blocked or the ductwork might be too small or restricted. If static pressure is too low, the ductwork might be very leaky or the fan might be dirty or damaged. We'll talk about that. Typical external static pressure totals are around 0.5 inches of water column or 125 pascals with an air conditioning coil or filter, and they're around 0.25 inches of water column or 62 pascals without an air conditioning coil filter. Right? And it is preferred to have the supply and return sides of similar magnitude, for example, a return of 34 pascals and a supply of 31. All right, basically this last bullet point is saying where the duct system installed correctly was it sized appropriately. If it was, the duct system should be similar in size. All right. Another test that we can take to evaluate duct system is a temperature rise test. And we kind of talked about that a little bit. We can actually use temperature rise in a formula that accompanies temperature rise to calculate airflow on the heating side. And basically to get temperature rise, we're going to take the thermometer and place it in the supply side as close to the furnace as possible, but out of sight of the heat exchanger due to radiant heat. We're going to use the manufacturer's recommendations, and we're going to use a 4-quadrant method, measuring at each corner of the supply plenum and averaging the readings. This is important. Your temperature, if you look at a duct system, if you place it in one location, airflow varies at different locations. It is a lot more accurate if you're able to get different readings and average those together to get an accurate temperature, right? And average those together. You're going to place the thermometer on the return side. You're going to fire your equipment, and when equipment reaches steady state, you're going to subtract the two, and that's how you get your static pressure. Now, for forced air furnaces, manufacturers produce a static pressure data tag, a number on a data tag that helps you understand if the furnace is operating within a static pressure parameter. And they give you a range. If you're operating on a high side of the range, you may have a duct system problem. It could be an equipment problem, but you may have a duct system problem. All right, here's a visual representation of that temperature rise test. All right, taking my supply air here. And remember, for best results, get multiple temperatures inside that duct. If you can get the probe in different lengths inside the duct, that gives you a more accurate reading. All right, same thing for the return. Add the two together, and then when I add the two together, it gives me my temperature rise. So in this case, it's 70 degrees. All right. Excessive temperature rise can result from the wrong fan speed, bad motor bearings, low voltage to a motor, dirty blower wheel, wrong motor rotation, and slipping blower belt. All right. Low airflow from restrictions in the system. If I got undersized or restricted ducts, dirty filter, or clogged cooling coil is going to affect my static pressure and my temperature rise. You can also have a high temperature rise from a burner being overfired, such as a gas pressure issue or maybe the improper oil nozzle size. All right. Low temperature rise can come from excessive fan speed, excessive duct leakage, underfired burner, such as low gas pressure or improper fuel oil nozzle. All right. And then the fifth test for static pressure is that if it's too high, it can damage the heat exchanger and cause rocking on the limit. And what rocking on the limit is, the limit will excessively cycle. So the customer will be calling for heat and the equipment will run and then it will shut off on limit, even though there's still a heating demand. Over time, that limit will fail. And as we teach technicians, if that limit failed, it failed for a reason. There's something causing that limit to fail. We need to investigate the problem, and it could be the duct system. All right, temperature rise that is too low can lead to condensation on the heat exchanger, which isn't good, cause excessive soot buildup, and lead to occupant discomfort. All right, our next duct system evaluation tool is measuring airflow. You can measure airflow really quickly with a lot of tools that are on the market these days. This is one of them. You can get static pressure and airflow in about 5 minutes. It is really easy to evaluate duct systems to let you know if you have a duct problem and if they warrant the other testing methods that we talked about. So a really nice tool to have. Right. Some manufacturers will give you the input of a piece of equipment along with a recommended airflow, right? So looking here, we already have those rules of thumbs for the airflow. Many people use a 350 CFM to 400 CFM per ton, depending on what you're trying to do and those conditions. But the heating side also has some recommendations also that sometimes the manufacturer will give you. Right? When you're evaluating the duct system, you always want to interview the clients. Typically, the clients are going to tell you exactly what the problems are, and you just have to listen to the client enough to understand what they're coping with. Ask about uncomfortable rooms, excessive noise, and frequent cycling of the furnace. These customers are experiencing this, and a lot of times, in my experience, it has been a duct system problem. And all the tools that we just talked about always have uncovered exactly what the problem was. All right. Look for things like disconnected ducts. Look for duct leakage, restricted returns and supplies, pan floor joists, ducts in unconditioned space that are not insulated, and improperly set balancing dampers. And also inspect the equipment. The static pressure starts from the fan. All right, you want to look at the blower wheel on the equipment. Is it dirty? All right, don't forget about your duct leakage testing, your pressure pan testing, your duct blower testing, your room-to-room imbalance testing, static pressure, temperature rise, and verifying blower CFM. These are the keys to evaluating any duct system, and by using these keys, you can uncover any duct problem and find out how to make that customer more comfortable and efficient. All right, strategies for duct repair. You want to write down the problems based on the readings. You want to determine required alterations for the furnace and ductwork, and then you want to decide with the customer, educated on what the best strategies are. Okay. And with that, we'll take some questions.
All right. So we have one question so far. So come on, everybody. Ask your questions in the panel there. This is a good one. How do you get a homeowner to pay for the pressure pan and blower door test?
That's a very good question. So these different tests are typically going to be used when you're trying to evaluate a problem. In my experience, what I've done, if the customer is experiencing a issue and they really want to solve it, and you have the data that they can show the customer that you can solve it, I've always started with measuring static pressure and airflow. It's a really quick procedure, and if the customer understands that the duct systems has an issue, a lot of times they are interested in having it solved. What you have to do to customers, you have to show them that they have a problem or that the problem that they're having has a solution. So showing them static pressure and airflow and how it's low typically opens up the conversation for them to pay for those additional tests.
Yeah, that makes sense. Do you I see a lot of people's homes where, they have those weird little diffusers on their grills. You know what I'm talking about? To
Hmm.
throw the air into the middle of the room. When you're doing these tests, you got to make sure all that stuff's kind of removed, taken away.
Hmm.
Right? Okay.
Yep.
Clarifying. Um, that's all we have, unless you have anything to add. Let's see. Oh, wait, they're coming in now.
All right.
Hold on. Um, I hate asking this way. But is there a rule of thumb for where to place balancing dampers? Should they be placed closer to the register or the supply plenum?
You know what? That is a very good question. Historically, I was always taught to place them by the supply trunk. But I'm gonna do some research on that one. That is a very good question. I've never heard that one before.
Okay, I'll flag
Yeah.
that one then to
Yep.
you. I have another individual asking about the slide deck. I know we did record this webinar and you'll have access to it afterward. I don't know how you feel about
Correct.
the slide deck. Do you want me
Yep.
to flag that one?
Table. Yep. Table that one.
I'll table you. And let's see if anything else came in. What do you think of a fresh air intake on a system?
Um, for ventilation, I see the purpose of it. I don't think that they work properly. When you set that up as a ventilation solution, that ventilation is hampered by the equipment operating, and you see a lack of performance in shoulder season. So let's say September in the Midwest region is pretty mild weather. You may not get adequate ventilation because equipment isn't working. So I typically don't like that solution. It is quite common. I've always been a fan of something with a fan of a fan, like an ERV.
Okay. This question: would you want returns on every room for changing air? Not sure if that makes sense.
Yes, it does. Yes, the only
Okay.
exclusions are bathrooms and kitchens.
Okay. Let's see. I think that is everything. Bryn, let's see. Did you want to let people know how to get a hold of you
Sure.
or your website even?
Absolutely. Website is www.hvactrain.com. And feel free to email me. I am Bryn at hvactrain.com. So BRYNN at hvactrain.com. And if you have additional questions or like to chat, we can definitely help you out.
Nice. I'm sure people would appreciate that. Okay, I'm going to wrap it up. For those of you asking about part one, I'm going to get to that now. I just want to thank everyone for being here, and of course for Bryn for sharing his insightful information with us. For those of you who want to view this later, I'm going to show you how to get to that on the website. So if you log into rses.org and you click on your homepage, so if you hover over this training tab, so sorry, everybody, get me back to the homepage. Give me a sec. And then you click webinar archives. You'll see Bryn's part one is right at the top, and then you can go through and look at all the other webinars that we have available as well. So those are free to view for all you members. And then everyone who attended tonight's live session, as soon as I end this, you are going to get a continuing education for 1 hour certificate that will show up in email. If you guys have any questions or you have any suggestions for additional topics you want to see, you can contact me at general@rses.org, or you can give us a call at headquarters. Thanks again, everybody, and I hope you have a great night. Thank you, Bryn.
Take care.